Welcome to this last theme in our module, Nuclear Physics. In this theme 4.1, we're going to talk about the nucleus, fission and fusion. We're going to set up the terminology that we use to begin with, talk about binding energy and mass defect, the fact that mass and energy are interchangeable via Einstein's famous equation equals mc squared. In the nucleus, we've got a bunch of positively charged protons. Shouldn't they repel? Well, there's a force holding them together called the strong force. And we're going to turn to energy from the nucleus via fission or fusion. We're going to describe what that means and the fact that fission has strengths and weaknesses. We would really love to do fusion, and it's an engineering challenge more than anything that's set out before us now to achieve that. Have the notes open, be annotating on them as you go through this lecture. I recommend that strongly. Also recommend having Wiley open in a page, chapters 42 and 43 for this part. It's very good to stop the lecture and have a read of that around the lecture, led by the lecture notes as to what you should be looking at in Wiley.
Radiation, as we refer to it, comes in three forms: alpha, beta, and gamma radiation. Alpha and beta radiation involve particles that have mass. Gamma radiation involves photons, which do not have mass. Alpha radiation is helium particles without the electrons, so it's helium ions, if you like. Beta radiation is electrons, or the positive charge equivalent of electrons, which are called positrons. The earliest experiments for discovering the nucleus performed by Rutherford, Geiger, and Marsden. They fired alpha particles at a gold foil. They collimated the alpha source with the use of irises so they could know its direction, and then they looked at the angle of the alpha particles that had gone through the foil. Illustrated on the right hand side, you can see that, well, at least as illustrated, most of the particles have gone through undeviated. That's reflected in the graph in the center, but it's on a logarithmic scale, so at first sight it doesn't seem that. But if you think about the logarithmic scale, have a closer look. It's falling by a factor of 100 in particles detected within about an angle of 10 degrees. So if you plotted that on a linear scale, you would conclude that basically most of the particles are going forward undeflected. So what do we learn from that? Well, we learn that the nucleus is concentrated very much at the center of the atom. It's an incredibly small part of the atom. You could consider the size of a typical nucleus to be that of a tennis ball relative to a football stadium. It's 10 to minus 4 of the Bohr radius then for a hydrogen atom. The simplest way we could think about a nucleus is a collection of nucleons, that's protons and neutrons, and the volume of that would be proportional to r cubed, and the volume would also be proportional to the number of those nucleons. So we can write an equation on the left: r equals little a, constant of proportionality, times by capital A, the so-called mass number, that's the number of nucleons, to the power 1/3. And little a turns out to be around a femtometer. A femtometer is 10 to minus 15 meters. First, some terminology. Z is the proton number, or atomic number. N is the neutron number, or number of neutrons. A is the mass number, which is the sum of those. Protons and neutrons are both called nucleons. And if we want to write down an element, we write it like this with the periodic table term Au for gold here. Has a mass number 197, that's put top left. And with that, we can know everything about this in terms of protons and neutrons. We can look up gold on a periodic table and see that it's 79th in the periodic table. That means it has 79 protons. And the number of neutrons it has is the difference of this mass number and the proton number, which is 118 here. And we could have different isotopes of gold too. There are two examples given there. They would have different mass numbers then, but not different proton numbers. Why don't nuclei break apart? You have positive particles, which are protons, and neutrons are neutrally charged. So overall, you've got a fantastically strong repulsive force there at that close range. So why do they stay together? Physics needed to evoke a force for doing that. It's called the strong force, and it only works at very short ranges. You can think of it like a glue. Let's think about units. We're dealing with very small masses, so it makes sense to have a unit for that. One atomic unit is 1.66 times 10 to the minus 27 kilograms. It's almost the mass of a proton or a neutron, but not quite. It's based around the definition that the mass of one atom of stable carbon-12 is 12 atomic units. Why define it like this? Is because carbon-12 can be readily produced around the world to a high standard. And so it makes sense to use that element for an international unit. Let's also think about the kilogram unit itself. We can express mass in alternative units of energy divided by c squared. Energy can be in joules, or it can be in electron volts, or in this case, mega electron volts for nuclear physics. So it can be in units of MeV over c squared. And we can do that from Einstein's famous equation, E equals mc squared. If we take one atomic unit, 1.66 times 10 to the minus 27 kilograms, and we times by c squared, we get an energy in MeV, and it's 931.494 MeV. Nuclei decay from unstable forms to stable forms. And we can see that the more stable form of a nucleus has more neutrons than protons in it. And as the atomic number increases, the neutron number increases disproportionately. No discussion about stability would be complete without talking about energy. A more stable form of a system has a lower potential energy. To split apart a nucleus, you have to put in energy to do that. And if you were to take every nucleon and completely separate them, we would need to put it in an energy which we call the binding energy of the nucleus. It's the energy added to break it all apart. How could we, in principle, measure nuclear binding energy? Well, we could take a nucleus and we could measure its mass before and after splitting it apart into all its constituent nucleons. The mass before would be capital M here, and the total mass afterwards would be a sum over all the nucleons, all the nucleon masses. If we times these masses by c squared, we get this energy required to take the system from one state to the other, the binding energy. We can also consider the binding energy per nucleon as a useful number. We take that binding energy and divide by A then. And that represents the average energy holding each nucleon to the nucleus. That difference in mass between before and after is commonly referred to as the mass defect. We take that mass defect and times by our conversion factor we talked about earlier, and we can get that binding energy in MeV quite directly that way. Okay, so let's do an example for deuteron, which consists of a proton and a neutron, has an atomic mass of 2.014102 atomic units. We're also told that the mass of a proton is given there, and the mass of a neutron we're told too. You can see they're very close to an atomic unit, but not quite. And they're not quite the same mass as each other either. So to find the binding energy of a deuteron nucleus, we take the mass that we have after the total mass of the system, which is one proton and one neutron, and we take away from that the mass of the deuteron nucleus at the start. We can times by 931 MeV per atomic unit that we talked about earlier, and we conveniently convert that to an energy in MeVs. It's just over 2 MeV. Here we have a graph of binding energy per nucleon versus mass number for all the elements. It's pretty instructive. It's got iron at the peak there of the graph, and it's very ordered. I suppose those are the two things one would note. If you're on the left side of the graph, a light atom will fuse with another light atom to the left of iron, releasing energy. Energy would also be released from an atom that's heavier than iron if it splits apart, so undergoes fission. So there are two means by which energy can be released. Heavy atoms split apart, light atoms fuse. We ought to reflect on this unit, mega electron volts, MeV. At the beginning of the course, theme 1, we talked about quantum mechanics. We talked about the quantum levels that exist in a hydrogen atom, and we used units of electron volts. They were very convenient units for that, for energy. Here we're using mega electron volts, and I draw that difference 1,000,000 times, or at least 100,000 times the energies are involved in changes that a nucleus undergoes relative to the changes that bound electrons undergo around a nucleus. Chemical reactions involve changes in electrons around a nucleus, and the energies involved in those changes on the scale of electron volts. Nuclear reactions, on the other hand, involve changes of the nucleus itself, and the energies involved on the scale of mega electron volts, 1,000,000 times as much. We can see that playing out when we consider the energy released by 1 kilogram of matter for different things. If we consider something mechanical like a kilogram of water falling 50 meters, we could run a 100-watt light bulb for 5 seconds. If we consider oxidizing carbon, so burning coal, kilogram of that, 8 hours. And as we come to nuclear reactions, it's quite a leap. 1,000 years for fission reactions, uranium oxide. If we go further to complete fission and complete fusion, we're looking at tens of thousands of years to run a 100-watt light bulb. If we could completely annihilate matter by bringing antimatter and matter together, we can do that, although it's not a practical proposition at this time. But we're looking, so that would be Einstein's famous equation E equals mc squared, and we released all that energy from that mass, we'd be running that light bulb for 30 million years. Let's consider an example fission reaction. A slow neutron meets a uranium-235 nucleus. The nucleus is raised to an excited state by that as uranium-236. It then undergoes fission. It splits apart, and there's a range of daughter products it could split apart to, and that's shown in this graph. There must be conservation here of protons and neutrons involved in this process. And here's an example of two daughter products that are at the peak of those curves, xenon and strontium, and also the release of 2 neutrons. So strontium's at mass number 94 and xenon at 140. Both of these daughter products are neutron rich, and from what we were saying in part 2 of nuclear, that means they're going to undergo beta minus decay. And that's what they do. Xenon turning to cesium, to barium, to lanthanum, to cerium, which are an increasing quantum number, increasing Z, and the same for strontium to ytterbium and then zirconium. The half-lives constantly increasing as you go along, as the elements become more stable, and they reach that line of stability that we were talking about, where the stable elements lie, where the ratio of neutrons to protons are optimum. So how may we think about this nuclear fission reaction? Well, the slow neutron is absorbed into the 235 nucleus. To have a high chance of absorption, it does need to be a slow neutron and not a fast one. It results in an unstable nucleus, which ultimately is going to split apart. You can consider it as vibrating violently until it does. So there's some time scale to this happening, but it's inevitable that it will split apart. And when it does, 2 neutrons are released in the process as well, stabilizing the nuclei. What's the energy released by fission? It's the total final binding energy minus the initial binding energy. And that can be rewritten as the final binding energy per nucleon times the final number of nucleons minus the initial same. In an example question here, we've got a fission of a high mass nucleus, mass number 240, binding energy per nucleon 7.6 MeV per nucleon, and it splits into 2 middle mass nuclei, mass number 120, with a higher binding energy, 8.5 MeV per nucleon. So it's a higher binding energy, and as we said earlier, we can expect that relates to a greater stability. If we put those numbers in, we get an energy released of 200 MeV. Returning to uranium-235 and its absorption of a neutron, if we look at the mass defect for that, the mass defect is negative. So energy is released by taking on board that neutron, and it's that which fuels the vibration, which ultimately splits the uranium-236 apart. A nuclear reaction can run away with itself. And here we see this equation pointing to that. A neutron is absorbed into uranium-235. It then results in daughter products, a massive release of energy, and a growth in the number of neutrons, which can go on and do likewise. So we have the potential for a runaway reaction, more neutrons at the end of that reaction than we started. For a nuclear reactor, we would like to sustain the number of neutrons that are causing fissions to a steady number. We would call that reaction critical, a steady state power operation. If it's less than 1, the ratio of thermal neutrons after the process to beginning, we'd say it's subcritical. And if there's a growth in the number of thermal neutrons in this process, we'd say we're going supercritical. Now, we're focusing to thermal neutrons in this process because thermal neutrons, in other words, neutrons that have only a low kinetic energy, are absorbed more easily by uranium-235 than fast neutrons or high kinetic energy neutrons. So thermal neutrons really read low kinetic energy neutrons. Okay, well, if we start with 1000 thermal neutrons, for example, and impinge on our fuel here, uranium-235, we would expect to see a growth in the number of neutrons following fissions from this equation. So we have a growth here, and we have an example, 30 fast neutrons here now. Okay, but they're fast, and that's not so useful for sustaining a steady reaction. They would need to be slowed down, so that's a process we need to actively control if you want to have a steady reaction. Uranium-238 is certainly in the mix. In fact, it's most of what the fuel is made of, and that contributes energy and fast neutrons too in a fission. But it's important to get a sufficient ratio of uranium-235 to uranium-238 for this process to work effectively. Okay, so we've got fast neutrons here anyway at this point, and we're going to lose some neutrons on the way by various means. So the number comes down. But the key step here in green is to control how we take those fast neutrons and slow them down so that they become low kinetic energy or thermal neutrons. We can do that in a controllable way. Heavy water is used in nuclear reactions, and that naturally slows down neutrons when they interact with it. And for a controllable way of adjusting that process, carbon rods are generally used, inserted into the reaction, taken out. So moderation is via both. We end up with slower neutrons as a result of those collisions, and then we can carry on around the cycle again, and it will be a self-sustaining cycle releasing large amounts of energy. In a pressurized water reactor, pressurized water takes the heat out of the reactor. So this is hot pressurized water. We remove the heat from that water before returning it using steam, pressurized steam, which drives, on heating it, drives turbines, generates electricity, and that steam is returned. It's important that that hot water in the reactor doesn't mix with the outside world, and this process, if its integrity is maintained, of course, should do that. We have to ensure that that integrity is maintained because nuclear waste can remain active for a very long time. And here we see thermal power generated by radioactive waste over a period of time, logarithmic scale. So it looks sort of linear, but in fact it is falling off a lot faster than that. But point being, radioactive waste remains dangerous after a long period of time. Fission is challenging then, in that the products formed from fission remain active, radioactive for long periods of time and therefore pose a health risk. So there's great interest in thermonuclear fusion as an alternative. It's very difficult to achieve from an engineering point of view. Nonetheless, if it's possible to sustain thermonuclear fusion, the daughter products do decay quickly and therefore it's a lot cleaner. To do this, we need to have atoms close together. We need to have a lot of them close together, and they need to be of high temperature. If we heat something, the average temperature of a particle is given by Boltzmann's constant times by temperature in Kelvin. On the Earth's surface, average temperature here means things have an average kinetic energy, or molecules do, of 0.03 electron volts. At the Sun's core, we're looking at 1.3 kilo electron volts. That average energy itself isn't enough to fuse cores together, but the distribution of energies at the center of the Sun is such that there are energies, there are nuclei with much higher kinetic energies in the tails there, and they will have enough to have an opportunity for fusion. The Sun is a role model for thermonuclear fusion, so let's look at how it does it. We start here with two hydrogens fusing to form deuterium, and let's consider that happening in parallel, each releasing a megavolt of energy, and then we take the deuterium nuclei formed by that, plus another hydrogen to form tritium. Consider two of those happening in parallel, 5.5 MeV released by each of those, and then we fuse two tritium nuclei to form a helium nucleus and two hydrogens. We can summarize that for the nuclei as 4 hydrogens fusing to form a helium. The energy released by this overall reaction is the mass defect times by c squared. So if we take the mass of helium minus the mass of hydrogen times by 4 and times by our conversion factor, we get 26.7 MeV. You can easily see that by taking the energy released by each step of the reaction in the previous slide and adding them up. Comes to the same value. Now a little bit of that energy is released in a form that is not as heat, it's as neutrinos. We've mentioned them in part 2, and they stream right through us and right out the other side of the Earth. Fascinating particle, but not a subject for this course. The rest is deposited as thermal energy in the Sun and ultimately wakes its way out as light. So the Sun's been burning for 5 billion years, and we reckon we got 5 billion to go. So can we copy the success of the Sun? There certainly is a large effort underway fusing deuterium, tritium to try to do that. Doing that in a controlled way, releasing a large enough rate of energy is the challenge. For that, we need to sustain a high density, high collision rates, and a high temperature. This leads to Lawson's criterion that n is density and tau is the time that particles are together. We need that high density maintained for a sufficient length of time that particles can meet and fuse. A plasma is an extremely hot form of matter, up to millions of degrees Celsius. So to contain it, it's very difficult to have it in physical contact with materials. Magnetic confinement is one way that's being tried to do this. A toroid, basically, that we talked about earlier in the course on the magnetic part of the course, is used to confine what are charged particles here with high velocities to spiraling around magnetic field lines in a big circle. Another method that's being tried is inertial confinement using high-powered lasers to zap a pellet from many sides at the same time to cause an explosion around the pellet, which then drives the center of the pellet into fusion.
So I hope this has been helpful. We've talked about the interchangeability of energy and mass, and the force that holds the nucleus together. Talked about two ways of getting energy from the nucleus, fission and fusion, and the fact that fusion is the holy grail of what we'd like to achieve for sustainable energy for our futures. It's time to turn to the homework problems now, so have a crack at those.